One for this webinar series on acoustic, mechanical and thermal metamaterials. Today we have the great pleasure to welcome Vincent Pagneux from the Laboratoire of Acoustics and Mechanics of University of Le Mans near Paris. And Vincent is going to talk about reflectionless modes, an alternative spectrum for wave scattering. Professor Pagneux.
Thanks a lot. So first of all, I would like, of course, to thank the organizers, so Bogdan, Mohamed, and Sébastien, for inviting me in this very always interesting series of webinars on all aspects of waves and propagation in complex media. So I'm very pleased to be part of it. And today I will talk about scattering problem and some illustration of a spectrum that is alternative and as such different from the classical quasi-normal mode spectrum. So it's another set of complex frequency that gives information for the scattering. And so this work is a collaboration with Anne-Sophie Bonnet-Bendia from ENSTA in Palaiseau, and Lucas Chenel from INRIA, as well in Palaiseau. And this is a collaboration between more wave physicists, myself, and these two collaborators that are more in applied math. So maybe you have seen parts of their talk. They have presented already some part of the talk in a more applied math fashion. But here I will go more in illustration and more trying to get some physical hints of what's going on for the scattering. Okay, so the subject is coming from the reflection that in many situations for scattering, it is the transmission that is of interest. And so here are some illustration of that in a waveguide, in a junction of waveguide, or in grating, or even here a waveguide coming in some infinite space, so baffled waveguide. In many of these situations, so in all these situations first, something important is that it's possible to separate the space in at least two disjoint domains, where in one domain there is an incident wave here in red and reflected wave in green, so in domain incident, let's say, and there is at least one other domain disjoint where we can call a wave as transmitted. And in all these situations, very often, what is at stake and what is the subject is to find situation when it's possible, where it's possible to transmit either perfectly or at least to have good transmission. So going into that direction, here is, for instance, a list of some occurrence of this interest of good transmission. So, of course, perfect transmission resonances belong to that. So it's in this layered media, it's often a question how to be able to construct a layer medium with perfect transmission resonance, meaning complete transmission, perfect. After you have the extraordinary optical transmission, EOT, where transmission is the central subject. Even in disordered media, we know that it's possible to find transmission eigenchannel. That's meaning that if you select very well the incident wave, and if you select the good channel in the multimodal propagation, it's possible, choosing this good eigenchannel, to transmit even if the medium is opaque. Metasurface and metamaterials in general, often the subject is to get good transmission. And for another recent example, even in topological wave, the question of immunity to backscattering is a problem of transmission, and this immunity to backscattering means that we are happy if we are reflectionless. So, just first a short reminder for the definition of transmission and reflection. So here I will focus, because it's a good example of the subject on waveguides. So here it's a sketch of waveguide setup. So we have a waveguide center. We are solving the wave equation, meaning the Helmholtz equation, with an index n that can depend on x. And we can have scattering by the scattering center, either by homogeneity in the index n, meaning that n will not be constant, or it can be also scattering just by the obstacle or inhomogeneous geometry. Okay, so there is this scattering center, and we send a wave called here A in on the scattering center. From this incident wave, there will be two outputs. One output reflected, A out here, so it's coming back in the same domain as the incident wave. And there will be a transmitted wave on another domain that is called here B out. And then from this two outputs, we can define the transmission and reflection coefficient. So naturally, the B out goes to the definition of the transmission. So B out is transmission times incident wave, and A out is the reflection. Now, how looks a typical transmission spectrum? So I call it abusively a spectrum, but it's just the transmission coefficient as a function of frequency. So usually it's something that is with a very complex behavior. And often we see peaks in transmission that are either going to perfect transmission, and as this peak here, this peak's going to transmission equal to 1, so it is perfect, everything is transmitted. Or we can see transmission peak here that have good transmission, but it's not exactly going to 1. So to try to get a tool or something that is able to be useful to understand this transmission behavior, a very classical tool is composed of what is called complex resonances or quasi-normal mode, QNM. So I will use in the following both of the name. So this QNM, they correspond to, they give, I will define them later, but generically, the QNM spectrum, it gives a set of discrete eigenvalue in the complex frequency plane. So here, maybe I didn't mention that, but I will also call K the frequency. And so as a solution of this Helmholtz equation. So this QNM spectrum, it is a set of complex K eigenvalue. And generically, so here it is, so we have to go into the complex plane real K, imaginary of K. And with the, here I am choosing the convention of harmonic regime exponential minus I omega t. All these QNM, they will have imaginary part of K negative. We'll see that a little bit later. Okay, so we have the transmission as a function of real frequency for a regular scattering problem. We have this QNM spectrum, and then this QNM spectrum is often interesting because there is a correspondence between transmission peak and this complex frequency resonance. So here, for the same situation, I have here plotted the transmission as a function of real frequency. And below is the complex frequency spectrum of QNM. And we can see that, so, as here in the complex frequency plane, I have this blue horizontal line for real frequency. So we see that when the QNM are close enough to the real axis, they are able to predict quite well the transmission peak. So here, this 3 perfect transmission are quite closely following this the position of this 3 QNM. But this peak here does not correspond to these 2 complex resonances. And we can call this pair of complex resonances some kind of hidden complex resonances. And usually this QNM can be hidden when there is a strong overlap between different QNM, meaning that the imaginary part of the complex resonance is larger than the spacing between successive complex resonance. So, or to make it simple, when the QNM are too far from the real axis here in blue, when they are too far, it becomes more and more difficult to relate them directly to the transmission behavior. Okay, so this few words on how is defined this QNM quasi-normal modes. So first, so here it is a sketch of a waveguide with an obstacle in gray. So they are defined as a solution of the wave equation here, Helmholtz equation, with only outgoing wave. Okay, and so how to make it an eigenvalue problem? There it is fairly simple, owing to a very nice technique that is called perfectly matched layer, or as well could be called, was called as well complex scaling. And this perfectly matched layer, you just put them on outgoing parts. So you want outgoing boundary condition at left and right. And at this left and right, you put this layer of this perfectly matched layer. You put them, and they have the very nice property of being not implying reflection of the incident wave and attenuating the wave at the same time. And so they are able to model very well the condition of outgoing wave. That is, if we forget this technique, that is usually quite difficult to model. So here with just these 2 layers in green, these 2 PML, we have an eigenvalue problem that is just as in a cavity problem. You solve the wave equation and you look for the eigenfrequency k. And just you have to put these 2 green layers. So this problem of QNM, it looks like scattering, in fact. But the only thing missing from the scattering problem is the source, is the ingoing wave. So that's why it's so important. It is really, in that sense, normal mode of the scattering problem. The incident wave usually are the source exciting the wave, and here you put off the source, and you just have this outgoing wave solution. So it's without right end term of the wave equation in some sense. Okay, so this QNM problem, as we can see here with these 2 PML correspond to loss. And so it is a non-Hermitian problem, but with loss. And so it gives eigenvalue in the complex frequency plane because it is non-Hermitian. Something important here is to notice that since the loss, it's only loss everywhere in the system, so it is loss radiative. The wave is able to leak away from the scattering center. Since there is only loss in the problem, the imaginary part of the eigenvalue k can be only negative. Okay, so once we have this quasi-normal mode spectrum, so it's very nice because we have, in some sense, the map of. So you have your geometry, you have your index. You compute once your spectrum. It gives you value in the complex frequency plane, and it gives you a map of what will be the event or the resonances of the scattering. So it will give you really where it's possible to get wiggles in transmission or reflection. So it's why it's very, very nice. However, if we are really focusing on perfect transmission or even good transmission, it's not directly given this information. And as we have seen already previously, it's even possible to have hidden quasi-normal mode when the overlap is strong enough. So that's the subject, is how to go more directly to very good transmission. And I call it reflectionless because to get perfect transmission or reflectionless here, it will be the same. Just to be noted as well that this hidden quasi-normal mode has been the subject some years ago of these two papers, more particularly for disordered media. So they were exhibiting hidden quasi-normal mode in disordered media, and they were able to show that a good fraction of all the QNM, they were hidden, and they were even getting the average ratio of this hidden QNM for disorder. And so here we will go even for non-disorder, complex but not so complex as disordered, and we have seen that hidden QNM can exist even in that case. Okay, so QNM we have seen that it's useful, but it's not directly going to transmission, and then now is going the spectrum that is an alternative to this quasi-normal mode. So actually it's very simple. Starting from the definition of QNM, where we know how it works and how it's easy to make it an eigenvalue problem. So here we have the QNM. It is solution of the wave equation only with outgoing wave equation. If we are interested in good transmission, then just by reversing for instance, here at left, reversing the condition. If we say that at left, we want just ingoing wave, and at right, we want only outgoing wave, it will be by definition a reflectionless mode, because here we impose that there is no reflection. And so that will be the main idea of this reflectionless mode, to look for solution of the wave equation that are with just ingoing wave at left like that. So of course, so here it's defined from left. So there is a left reflection mode, but you can define in the same way a right reflectionless mode. Okay, so it's just a question of reversing one of the two parts and how to make it an eigenvalue problem. In fact, it's very simple as soon as you know how to compute quasi-normal mode. Because, okay, so we want a solution with outgoing wave on one part as for quasi-normal mode. So we put the same PML as usual, corresponding to loss here in green. And to impose ingoing wave at left, then you just look at your PML and you can see that if you complex conjugate the PML, you reverse as well the direction of the wave you impose. And so taking a conjugated PML will impose, instead of outgoing, purely outgoing, it will impose instead purely ingoing. And so eventually this reflectionless mode is just like that. You just take the classical PML on outgoing part and you take conjugate PML on the ingoing part. And so here, this reflectionless mode problem, it will go to a linear eigenvalue problem. It will be a non-Hermitian problem. Difference with QNM is that it will be with gain and loss. So loss on the radiative part where the wave can escape, but it will be gain on the side of incoming wave. So here it's really, you send the wave inside, so it's like a gain. So it will be with mix, gain and loss. As the non-Hermitian problem, this reflectionless mode will give eigenvalue in the complex frequency plane as well. But here, since there is both gain and loss, the imaginary part of K can take any sign. And so it's part of the funny game that we will see in the illustration. It can be on both sides, and it can be, of course, on the real axis easily. And so the eigenvalue on the real axis will provide directly perfect transmission. And just to insist a little bit, it's simple to implement because if you know how to compute a quasi-normal mode, you can compute reflectionless mode just conjugating one of your PML to impose incident wave. Then there is another aspect that is particularly interesting because of this mix of gain and loss. It is the case of spatial symmetry for the reflectionless mode. So here I have an obstacle that is mirror symmetric, meaning that it has the symmetry and the setup has the symmetry x minus x. And I have the gain, so ingoing at left and outgoing at right to define the reflectionless mode. If I am doing the P operator, meaning the x minus x transformation, so I reverse everything, so mirror symmetry. Okay, so it's different from the initial situation. But now if I am applying the complex conjugation corresponding in the harmonic regime to the time reversal operator, I reverse both the sense of the wave, so outgoing becomes ingoing and vice versa, but as well by complex conjugation, I transform the PML into conjugated PML and vice versa as well. And then applying successively this P operation in space and T operation for time reversal, I see that when I have a situation that is mirror symmetric in space, I come back to the initial problem, meaning that globally, this reflectionless mode problem is PT symmetric. So if we apply P and then T, we come back to the same problem. And so it appears that this reflectionless problem, eigenvalue problem, is PT symmetric. So why it is interesting? It is because these PT symmetric non-Hermitian eigenvalue problem have very strong property. And so the major one is that the spectrum will be stable by complex conjugation, meaning that if you have a mode with complex eigenvalue k, you will have also a complex eigenvalue k bar. And then we can discriminate between different phases in the jargon of PT symmetry. The symmetric phase when the eigenvalues are real, and then the eigenmodes have particular property as well. So here it will be the modulus of the eigenmode that will be mirror symmetric. Then when two real eigenvalue coalesce, so corresponding to an exceptional point of this non-Hermitian problem, we have what is called a symmetry breaking. And these two real eigenvalues are going into a complex pair in the complex plane. And it is called the broken phase, when the K become complex with non-zero imaginary parts. And what is very important is that this property of the spectrum in the PT symmetric case gives robustness, because if you have one perfect transmission for real K, so one eigenvalue for real K, this perfect transmission, if you change your system, but you keep the mirror symmetry, this perfect transmission can be lost only if it coalesces with another perfect transmission. So the perfect transmission will remain perfect transmission as long as you have no coalescence. So it's a strong robustness argument. Before going into the illustration, some related works in the literature, meaning some works I have found that are going into the problem of, okay, so how to relate perfect transmission to eigenvalue problem. So trying to avoid the quasi-normal mode. So as you see, so it started, for instance, more than 20 years ago. Most of them are for 1D problem. Many are for 1D lattice, so 1D discrete problem using the tight binding Hamiltonian formulation with effective Hamiltonian, etc. And the 2D is more recent with our work and other work this year. And just to stress, this work by Hernandez Coronado et al. Almost 10 years ago was the one inspiring us to go to 2D and this complex spectrum. They were using the same idea of PT symmetry, but they were not going into the complex spectrum. They were just going to real frequency eigenvalue. Okay, so now let's go to illustration of this reflectionless mode spectrum. First in 1D.
Sorry, Vincent, you did not specify the boundary conditions on top and bottom of your waveguide.
Which one? Here?
What would be the boundary conditions?
It will be Neumann boundary condition in general. But it doesn't matter. It could be as well Dirichlet.
Or Robin, even? It doesn't?
Yeah, it doesn't matter. In fact, the question is just, if you can compute quasi-normal mode, you will be able to compute reflectionless mode. It is exactly following the same step. You just conjugate one PML and you obtain this new spectrum.
And when you conjugate the PML, it means that on one side you have, well, decreasing modes, but on the other side they are exponentially growing.
Yeah.
So your eigenmode is decaying on one side, and it's...
No, it depends if you are in the symmetric phase or in the broken phase after. Because in the symmetric phase, you have this, for the PT symmetry problem, you have as well this property on the modulus.
Okay, sorry.
Okay, for the 1D, so the simplest is just to take the slab problem. So we take a 1D wave equation with an index n of x. N is equal to 1 everywhere except inside the slab here in color. And in this slab, the value can be different from 1. And then to compute the reflectionless mode, you impose the boundary condition of ingoing at left and outgoing at right, meaning that you impose this boundary condition globally. Okay, and then, as mentioned previously, if the index inside the slab is spatially symmetric, meaning that it is an even function of x, then the problem will be PT symmetric with this complex conjugation stability. Okay, so first remark, funny one, if you take index equal 1 inside the slab, so meaning that you take the free space, in fact, so you can. So you solve this reflectionless mode problem, and then you see that any exponential ikx is a mode, is a trivial solution. And so a funny remark is that first, for the trivial situation, the reflectionless mode spectrum is the whole complex plane. Every k everywhere is a solution. So there is still, if you take the trivial solution, it is amusing because you have no discrete eigenvalue. The whole complex plane is there. Okay. Then next remark is, let's go to the Fabry-Perot slab. So the very classical Fabry-Perot slab. So inside the slab, you take n equal n0, different from 1. Then in that case as well, we know everything. We know that we will have the Fabry-Perot resonances. We know the value. They are given by this k times distance equal m pi relation. And it means that, so it is a PT symmetric problem because the index constant is symmetric. And it means that for free, we have exhibited a PT symmetric problem with completely real spectrum. So it's not so It's quite funny because a lot of people have struggled to exhibit some problem PT symmetric with this complete real spectrum. And in fact, it appears that it is given directly by the Fabry-Perot slab in terms of reflectionless mode. Now we can complexify a little bit, and we can take the index inside the slab to be non-constant, n of x, but symmetric. So with the x minus x transformation. So it is an even function of x for the index. Now it is a PT symmetric problem, as we have seen, and it gives a complex spectrum with this complex conjugation stability. So the spectrum will look like that. Either the complex frequency will be on the real axis, giving a perfect transmission resonance at real frequency. Either you have pair of complex frequency like that are conjugate. Okay, and then last situation, if n of x is non-constant with no particular symmetry, we will just have discrete complex eigenfrequency everywhere in the complex plane. And the ones that are close enough or even exactly on the real axis will give good or even perfect transmission. Okay, so just a movie to illustrate. So here it's quite a tricky movie. It's for the case of a PT symmetry problem. So with non-constant n in the slab, but symmetric. So it is PT symmetric. And here I have tried to represent at the same time the complex frequency spectrum in red, so in the complex plane of frequency. And at the same time, here in blue, the reflection coefficient as a function of real frequency. So first, what we can see is that reflectionless mode. So and then I am changing the amplitude of the index inside the slab. So tuning the parameter, but keeping the symmetry. What we can see is that this famous property of PT symmetry, when you have a perfect transmission, so zero reflection, it is stable. And then after you see here the coalescence, and you see how from no perfect transmission, you go to two perfect transmission by the coalescence of two eigenvalue on the real axis. So here just before coalescence, so the two perfect transmission, so zero reflection here, and just here before coalescence of these two complex frequency, you see there is no perfect. And then after coalescence, you see simultaneously appearing two zero reflection, so meaning two perfect transmission. So really they are coming in pair for this symmetric situation. Now, little bit in the same spirit, here is an animation of for taking an index that is symmetric. So it is a PT symmetric case, starting from Fabry-Perot here. So here is the complex spectrum. Here is just the index as a function of space. Here is the complex spectrum in the complex K-plane with the reflectionless mode in blue and the QNM in red. And here is the transmission coefficient as a function of real frequency for the same problem. So when we take here, we will change the amplitude of the perturbation A that is non-constant and that is symmetric in space. For A equals 0, starting point is the Fabry-Perot. So you have this transmission here, and you have this perfectly ordered and with the same space reflectionless mode corresponding to the Fabry-Perot resonance. And then you have as well analytically the QNM that are just a little bit shifted into the im of k negative. And then we will make A increasing starting from 0 to see how is the behavior. So you see, so the spectrum is moving. So here the index is increasing, the perturbation is increasing. You see that the reflectionless and QNM are moving, and you see that here an event for the first perfect transmission here. You see that two perfect transmission are coalescing meaning two real eigenfrequency of the reflectionless mode are coalescing and go into complex pair. And what is funny here is that, okay, so they are complex conjugate, and one is dragging with it two QNM. So in red are the QNM. And so these two QNM that are brought by, and then they are going closer and closer to the reflectionless mode, they become hidden QNM. So here on this side, there is another event where you see also coalescence. And you see that here as well, we see this hidden QNM. It's always coming here. You see here, it's a little bit messy. You see this perfect transmission here and these three QNM that are difficult to relate directly to the transmission here. Okay, so it was for the symmetric case. Then another interesting case can be perturbation of the Fabry-Perot slab by a non-symmetric part. So here it is the sine function, it is odd in X. So it will not be PT symmetric. But why to choose that? And so it is very recent results, not well understood yet, but it's funny for me. At the same time, putting this perturbation of the Fabry-Perot, putting this perturbation, as you see, the index is here. It is in fact a finite periodic system with 4 cells. And we know that in 1D, if we take n cell, we will have n-1 perfect transmission for any 1D system. It's like that. So it means that this problem will be non-PT symmetric, but at the same time, it has to be able, we know that from 1D periodic theory, it will have to keep some perfect transmission resonance on the real axis. So it will have to keep a reflectionless mode eigenvalue on the real axis. And that's what we see. So starting from the Fabry-Perot, as before, we see just few eigenvalues leaving the real axis. So this one, for instance, leaving, and the other around that are remaining on the real axis. And the one leaving the real axis, of course, when we look at the transmission, we see what it corresponds to. What it corresponds to the band gap, the pre-band gap that is formed by finite periodic medium with 4 cells. And so we just see this perfect, this reflectionless eigenvalue corresponding to band gap leaving, but the other one are remaining on the real axis, even when there is no symmetry. It's still not well understood. Okay. So now I will go to the 2D situation with multimodal property. So what is, so we go from the ordinary differential equation world to the partial differential world. So of course it's more involved. And for waveguides, one of the novelty is that we have propagating waves and we have as well evanescent wave. And now when we define what is reflectionless mode, it will be one with incident propagating, no reflected propagating, and just transmitted propagating. But on the same time, there will be a near field, here in green, that will be composed on both sides by evanescent waves. So it's one of the new ingredients of the 2D system. So as said previously, so QNM spectrum, I will show sometimes QNM spectrum. It will be with loss PML on both sides, and reflectionless spectrum, it will be with conjugated PML with gain on the left and loss PML on the right. And so because of, so we have this evanescent wave in the leads of the waveguide. And so we will have cut-on frequency for each n equal n pi. So we will see some branch that correspond to this cut-on frequency. So another aspect of 2D is that there is a new ingredient as well. It is the possibility to get trap modes. So also they are known as bound state in the continuum, so BIC. And they are very funny solution because they are finite energy solution of the wave equation, even if we are in an infinite geometry. So really we have it's like a mode in a box. So it's finite energy, and it will be with a real eigenfrequency, real k. And this mode, they have no ingoing, no outgoing propagating wave, because if not, they wouldn't be of finite energy. So since they have no ingoing, no outgoing, they belong both to both the QNM spectrum and the reflectionless spectrum. And so they will appear when they are trap modes or BIC, they will appear on QNM as well as reflectionless. So here for so the first case I will consider is this pretty symmetric case with a mirror symmetric obstacle. So hard rigid wall obstacle, rectangular. And so the wave, so scattering or QNM for the wave around this rigid obstacle. So first, the QNM spectrum for this rectangular obstacle, here it is, so in the complex K plane, M of K negative for everybody as it has to be. So we see some branches starting from each cut-on frequency due to multimodal propagation. So here, this frequency range, there is one wave propagating. Here, there are 2 waves, then 3 waves, 4 waves, etc. And each one more wave on the real axis is marked by a cut-on frequency. And there is a branch corresponding to this PML and complex scaling. And that we have branches that are starting from each of these cut-on frequencies. Then here we can also see modes that are not belonging to the branches, and that are of interest for us today. And we can see 2 real eigenvalue. And so there are 2 trap modes in this situation that are illustrated here. So you see trap mode number 1 and trap mode number 2. So really modes of finite energy in this infinite geometry. Now we can compute as well the reflectionless mode spectrum, and we can see here, so in blue the reflectionless mode, and in red quasi-normal mode. So no surprise, the BIC trap mode, they belong to the 2 BIC, they belong to both spectrum. So they, in some sense, BIC are the common factor of QNM and reflectionless mode. And after you can see the difference. So in the first frequency range, when it is more monomodal, you can see that QNM are following closely the reflectionless mode. But after, in this PT symmetric, you have many other reflectionless situations. And you can see that the QNM are quite far away and are not able to predict easily this case of perfect transmission for some particular incident wave. So here, for instance, you have 1 QNM and 2 perfect transmission. So you see here one of the interest of this reflectionless mode spectrum. So some illustration of the reflectionless mode. So the 2 trap modes that have been shown already. And here the 2 first reflectionless mode. And you see here, so it's a wave coming through and able to be not reflected by definition. Just an animation to see how it works for higher frequencies. So here it's with possibly 3 propagating wave in the leads. And you see that here reflectionless mode. So here it is the reference wave. So just without obstacle, you see that before the obstacle, of course, it is the same because there is no reflection. And after the obstacle, you see a phase shift due to the obstacle. So there is no reflection, but still it does not mean that the obstacle is invisible because they can be phase shift due to the scattering. Another one at higher frequencies where it's multimodal. So you can see here the incident wave is composed of two propagating waves. And still you see that this reflectionless mode, you see that passing through the obstacle for this reflectionless mode means that there is a phase shift. Here you see a shift, but it is without reflection. And for this complex, more complex pattern, it is funny because we have the impression to understand a little bit how the wave is able to construct this reflectionless mode. Because here you see that this composition of two propagating waves is going to some nodes here, the nodes corresponding to the neck of the obstacle. So the wave is really adapting to the obstacle, trying to avoid where it can be very scattering. So a node, meaning that it does not feel well the rectangular obstacle. Okay, now we can go to the non-symmetric case. So non-symmetric in space, meaning that the reflectionless mode will be non-PT symmetric. Since the symmetry is as well absent for Y, there will be no trap modes generically. And the spectrum will not have the complex conjugation stability. So it is how looks the reflectionless mode spectrum. So here you see that, okay, so you have always this branch starting from the current frequency, but let's focus on the discrete mode along the real axis. And even if we are not symmetric, we see a lot of eigenfrequency for reflectionless mode that are very close to real axis. And they are still, even if not perfect, they can give very good transmission as seen here. So we take the first three close to the real axis eigenvalue. And you can see here also the pattern of these modes. And you can see here the reflection coefficient versus real frequency. And you can see that they provide a very good indication of very good transmission. So here is a reflection 0 here for that guy, here for that guy, and here nearly 0 reflection for that guy. And so even if there is no symmetry, it's still a tool able to give you a very good transmitting wave. Now, one question is that can be interesting is if we take something that is not resonating, like a junction, so here, this abrupt junction, okay, and then we know that it's possible to make it more adiabatic, less reflecting, just by making it smoother, more progressive like that. And we know that this kind of geometry is called adiabatic, more adiabatic, and it's because it is transmitting much better than the abrupt. So how it looks, so it is about transmission, so how it looks for this reflectionless modes. Here are the two spectrum for each situation. For the abrupt, you see few, not a lot of reflectionless eigenvalue. But when you take this smoother transition here, you see that this complex reflectionless eigenvalue are aggregating along the real axis. And so they follow this idea of adiabaticity, where you have more and more eigenvalue close to the real axis. Just for fun, another case symmetric, but here it's not with a mirror symmetry, it is with point symmetry. So this geometry here is symmetric with respect to the point, central point here. And so it is another choice of parity. And so still this problem is PT symmetric. And going to the reflectionless mode, it is PT symmetric, so it is with complex conjugation stability. We see here the mode in blue, and it gives you a lot of this reflectionless mode all along. So it gives you many possibilities to go through this double elbow geometry without being reflected. And so as well are plotted the QNM, and you see that they are not so good in providing the good transmission. So here is the illustration of the first 7 real eigenvalues that are reflectionless, so giving perfect transmission. You see from low frequency with planar mode incident to here multimodal that is able to go through this serpentine geometry without any reflection. One more illustration is what happens with more than 2 leads. So it's interesting because, in fact, when you have leads, each lead, you have the choice between choosing incoming or ingoing or outgoing wave. So it makes 2 choices for each lead, meaning that total you can define 2 power n different spectra. Among these 2 power n, one is with everybody outgoing. It is the QNM spectrum, the classical one. Then another one is everybody ingoing. It is the time reversal of QNM. So you just complex conjugate the spectra of QNM and you obtain this one. So it is some kind of absorbing system. And then, so it's 2, meaning that it remains 2 power n minus 2 reflectionless mode spectra, where you can play with sending on one lead and playing any game you want. But you have a lot of different spectra and a lot more than the usual QNM or even QNM plus time reversal of QNM. So you have more leads, more spectra. So here, just an illustration for a particular case with 4 leads, with an obstacle and to play with symmetry. So this obstacle is here, and it makes the system with these 2 diagonal axes as axis of mirror symmetry. So meaning that both are giving one PT symmetry. So this system is PT symmetric with 2 different axes. And so it is PT symmetric as well. And then computing the reflectionless spectra in blue compared to QNM in red, you see a lot of all these modes. And you see here illustration of one reflectionless mode at low frequency. So you send a wave from top and bottom and outgoing at right and left. And at higher frequency, you see that. So it gives you what is the incident wave to put on top and bottom to be reflectionless in this particular geometry. So I think I'm coming close to the end now. Maybe I will skip that part. And just before the final remark, just conclusion about the reflectionless modes. Of course, so by definition, what can be said is that it yields directly the well-transmitted incident waves, and more particularly the perfectly transmitted. It is designed to do that. So directly it gives you the frequency of interest if you want to be well transmitted. And one interest is that it is very easy to implement for anyone that is computing QNM. Because if you are computing QNM, you just have to conjugate some of your PML and you will get this new spectrum with this new property. And of course, still a lot has to be done with many open questions, as I was mentioning. Just after this conclusion, final remark about complex eigenfrequency. Often they are called unphysical, so not sure to understand what it means, but unphysical, but let's say that it could mean something that you cannot measure in experiment. But it appears that if you have a solution with complex eigenfrequency that is exponentially growing in time, it can be in practice, it can be excited by a starting source. So you start from 0 and then you make, so 0 difference between 0 and and very, very small value in practice does not count a lot. And then you start your source, and it's exponentially increasing. And then you will have an exponential source, exponential minus I omega t, with imaginary part of omega positive. And so it's really possible to imagine that. It is the idea of this recent paper 3 years ago to go to coherent virtual absorption for reflection. And we have tried to extend that to zero transmission, transient zero transmission, meaning that going to zero transmission or zero reflection, so here it's for zero transmission, we turn on the source and we make it exponentially growing to see what happens. And so it's a transient transmissionless system. And this is a joint work with Léopold Levé, Philippe Petitjean from MetaMAT's in ESPCI Paris, and Agnès Morel, Institut Langevin, as well in Paris. So how it looks, so it will be with experiment. Here is the setup. We have a cavity. We have so a cavity, and here we have waveguide on both sides, incident wave, reflected wave, and transmitted. When there is real frequency, okay, so we are on the harmonic regime, and then is installed incident wave in black, reflected in red, and transmitted in blue. So no loss, let's say. And then if we are able to get transmission that is zero for a complex eigenfrequency omega with positive imaginary part, that's an important point. We have to get complex eigenfrequency with exponentially growing source in order to turn on the source. So we can turn on the source, it's exponentially growing in time. And since by definition it is with zero transmission, you will have zero transmitted wave on the other side. So it's a kind of tricky transient harmonic regime with complex frequency. So how it looks. So here just a sketch of the geometry. From above, it is a channel for water wave. We compute the zero of transmission and trying to find the good. It's not so easy to find a zero of transmission with positive imaginary part. So playing with large cavity, it's possible. Here's the setup. Here's the wave maker. Here is the cavity. So we will see the numerical, the experimental measurement from above. And so with camera and projector, there are space-time resolved measurement of the surface water waves, meaning that we have the full measurement of the surface perturbation of the water wave, function of x, y, and t. And then for the wave maker, we decide to make it exponentially growing with this exponential minus I omega t with the omega that is complex frequency. So it's exponentially growing source. And
but you turn to the non-linear regime, là, no?
Yes, after you have to turn off at some point when it becomes completely crazy.
And I can see that you have a beach on the other side. So how much time do you have before, you see backward propagating, back reflected waves? How many wave packets?
From the beach?
Yeah, because I can...
The beach is good enough, and the channel is long enough to neglect the effect of the beach. The beach is quite well doing the job of anechoic. But okay. What you say is, the point is that, of course, you cannot exponentially grow forever, because you will go crazy and nonlinear, and so you have to turn off the source. So here is a spatiotemporal diagram. So time 0 is bottom, so time is increasing from bottom to up top. So here's the source signal. You see, you make it increasing exponentially, and then you turn off when you consider that your system cannot sustain anymore this amplitude. And here is the spatiotemporal diagram. So X horizontal and time starting 0 at the bottom and going increasing to the top. And you see that as long as you keep the exponentially growing, there is no reflection here. But when you turn off the information, time for the information to go to the cavity, and then there is a release of all the accumulated energy. So in some sense, the cavity is taking more and more energy, able to keep it. And then when you stop this exponentially growing harmonic regime, suddenly there is a relief of the energy. So here is the...
But the wave which is released, it has large amplitude. It's some kind of high amplitude wave, or I mean,
let's look at it directly here. Is the movie measurement of the
measurement?
Yes, it's measurement.
But it's a view from above.
Yeah,
you have to say it's a view from above.
It is surface water wave.
Okay, it's on the free surface.
Yes, so it is the elevation of the free surface. It is water wave, the same as in your kitchen.
Yeah, but people have to understand that your Helmholtz equation, it's with the velocity potential, in fact, the unknown.
Or even, let's say, yeah, it's the detail. It's with the surface perturbation even. But
yeah. But what I don't understand, okay, so it's great, and it's really a wonderful experiment. So you start, so you have your wave maker, and so the wave become
let's follow the movie.
Larger and larger amplitude.
Let's follow the movie here. So there is nothing. Then turn on the source, and the source will be exponentially growing in time. The wave maker is here, so it begins. So you see small amplitude, and the amplitude is increasing more and more at the wave maker. And then you look at the transmitted part, there is nothing.
Yeah.
And then it's accumulating energy inside. And then when you turn off the source, there is a relief of energy that was accumulated before.
And you have no back reflection. I'm amazed.
Yes. So after that, you are mentioning that, I suppose. Here, it's because we were as well going to tuning a little bit more in order to tune the zero of transmission. So the more difficult is really to get zero of transmission in this im of omega positive is very difficult. It needs really a 2D propagation here first. And then after, when we were able to get that, we were continuing the tuning to get the reflection zero at the same, around the same, and the most possibly close. And so meaning that we were in the situation where zero of reflection and transmission, they were at the same complex frequency. So meaning that's why it was without reflection as well.
And so here you assume some Neumann boundary conditions on top and bottom. I mean on, up, down.
On the vertical wall, yes.
Yeah,
because the setup is here. So surface water wave, it will go to a 2D problem. So it is constant depth when it is without at rest. It is a constant depth, vertical wall, and then it goes to Helmholtz equation with Neumann boundary condition.
But it's a first problem. So you start by finding these kinds of special eigenmode with conjugate PML, but now you have a first problem. So you have a problem with the source. Yeah,
because to make anyway, all the spectrum they are of interest, in my opinion, when you are able to use them for a situation with a source, because after, if there is no source, there is no wave. So,
can't you have some kind of wave tank situation where you would be in this situation of the existence of such eigenmodes? This would be a very long, but it would be treated as a wave tank without initiating any wave.
Sorry?
So you have a very long channel.
Yeah.
And you don't touch water. Yeah. Can you imagine that this kind of crazy eigenmodes are there? They are
the same as in any wave physics. If you don't put source, you don't have wave.
Yeah, but in essence, this resonance of your system is there. If it can be treated as infinite.
It is as there as any modes. If you take any cavity in any wave system in any domain, if you have a box in for Maxwell equation or for elasticity or for acoustics or Schrödinger or anything, you can always compute the modes, and the modes after will be the tools that you will try to use to describe the wave when there will be wave, meaning when there will be source.
But then your source, the way you choose your source is totally arbitrary. We agree with that. I mean, this possible wave, this eigenmode is there. It is in the wave tank already. It is there. Then the way, here you have a wave maker. This could, I mean, what would be the conditions on your source to be able to excite this eigenmode?
Here, this exponential growth has been chosen from the computation.
I agree, but it doesn't have to be a wave maker. It doesn't have to be a plane wave. Or does it, to preserve the 2D?
It is a plane wave because it is the zero, the mode zero, because it is Neumann boundary condition waveguide. So we are below the first cut-on frequency of the higher order mode. So in this range of frequency, there is no higher order modes. And by the way, it is finished for me. It was my last slide.
Wonderful talk. So now, obviously, it's time for questions, and you can ask, just like I did, any naive questions, that come to your mind to try to understand.
And even, and I would say, yes, and Sophie is still there, right?
I can check.
Yeah, because even